Okay, let's start. Do you have any questions about previous lectures? Uh, okay. So what have we learned recently? We learned that if there is some infinite space, we can use Fourier transform to compute the grain function of any equation and get some closed formula for it. Uh, but we also noticed that sometimes it happens that the same equation can be solved in several different ways. For example, we can solve it using the Fourier transform, like equations like this. Uh, mm, It can be solved using Fourier transform, but it can be solved just like just an ODE, or even simpler. If you consider equation like this, then it's obvious that it can be solved in some elementary way. So there's uh, so, okay, in this example, we realize that actually there is no need to take Fourier transform in all possible variables, and we can define a partial Fourier transform only in some part of variables. So, today we are going to study this, and I propose to do this because there are some phenomena that are easier to observe in this approach. And in some sense, it can provide us with a little bit more clear picture of what is going on and how the time evolution goes and so on. Uh, so I will have a function that depends on t and some space coordinates. And this partial Fourier transform is defined simply as this maybe let us use k as a subscript in this case. Oh, it was p probably. Up of t will be the integral over d and x e to minus I kx, or maybe k. I will anyway miss p and k all the time. And the inverse Fourier transform works absolutely the same. Here, and this time works as a parameter. And of course, we can write the same formula for finite domains. So this is for Rn. If we work with S1 to power n, then there will be u n tilde of t. Given as d phi 1 and d phi n over pi to power n from 0 to 2 pi in each variable. Uh, if we work on a square or on some rectangle, or then maybe how to write this better. Let us say that we have 0, 1 to power n. And then in this case, we choose different basis of functions, not such exponentials, but sines. Maybe let's take it from 0 to pi. So there's of course a question about normalization, but let us choose it in some random way. Maybe again to pi, or maybe just pi. Maybe let us call this variables axis because they are not periodic. These are functions of orthogonal. Those are orthogonal functions on this n-dimensional cube. Of course, we can choose different sides and so on, but the idea is always the same. And well, we can also write it for the half line. Again, with some sine functions, but with infinite integrals. We can combine these cases, so there is something. So whatever Fourier transform you can imagine, you can write it for this space coordinates. But the main idea is that if you act with some shift operator or with derivative operator on this partial Fourier transform, and this operator acts on coordinate part only, then it produces a function of k. So we have this formula for u uk tilde, but if we replace u of t and x with dx I squared u of t and x, what happens? We have the same integral. that can be computed by integration by parts. So, what we'll get if you integrate this integral by parts twice? Yes, which k? K is just a square of this derivative. Mm-hmm. Yes, yes. Minus ki squared. Mm. Well, let us write it as a prefactor. So this is minus ki squared uh, u tilde k of t. So this is where u tilde goes when we differentiate u. And we can also notice that this works equally well for functions like this, because when we differentiate sine twice, it is again sine. So there is this slight update as compared to the usual idea that we should diagonalize shift operators, that we can diagonalize a square of derivative, and the eigenfunctions of this operator are more general. They are not just exponential, they are linear combinations of positive and negative exponential, like sine. So, and the same happens with shift operators. So, in the functions in this one and this line, n is a vector in z and z, right? Yes. Where is so the variable in the at the bottom of the field? Not as an argument. Because we will see that so in our consideration this n will serve as the index. Our equations will separate into independent equations for each value of n. So. The same. What is? Hmm? But so what is unfamiliar that we can put real vector as the index? But it happens quite often, but maybe in physics. So that's. But here it is. Yeah, probably I should have written who this index is. So in this case, it corresponds to Rn. In this case, it corresponds to Zn. And in this case, it corresponds to Z greater than 0 to n, this quadrant to because n equals to 0. If at least one of them is 0, then this function is 0. So there's a Fourier transform adjusted for 0 boundary conditions at both boundaries. Okay, so any other questions? So we see the derivative operators are diagonalized, and we can check in the same way that symmetrized shift operators are also diagonalized. In a sense that if we consider u of t and x goes to u of t x plus a plus u of t and x minus a, and then u tilde k of t goes to um, to sine of ka times u k of t. So all these operators are diagonally, and now let us apply this to our equations. So what do we have in the list? We have the wave equation. Minus Laplacian of u equals to, let us put some function here. And since we are not performing Fourier transform in time, we don't care about this. We can say that t is greater or equal than 0, and we have some trivial boundary conditions, initial conditions. We also have the heat equation. And actually we also have a Laplace equation, and it is interesting to study it if we consider one of coordinates separately. Because the only difference between the Laplace and wave equation is this sign. Or we can say differently that the only difference is this sign. We can write it like this. So let us try to study the Laplace or Poisson equation in this form. So let us write uxx plus Laplacian of u, when Laplacian means Laplacian in all other variables, equals to f. But interesting what happens when we perform this change of sign. So, or maybe, no, maybe I don't want to change on that sign. I'll better change on this one. So the picture is like this. We have a semi-infinite space, semi-infinite time, and some space coordinate here. It can be either the whole real line or just some interval, or it can be closed. The point is that the solution works, this equation works in the same way. So let's perform this partial Fourier transform. So time derivative commutes with this transform. So Laplace operator, even if it is some difference Laplace operator, acts by some number that depends on k. And let us denote this by this number by k. So the same. So sorry of x. So now the question is.
I don't understand. Before we said that the Laplacian transform to the shift operator. Why we are not using substituting the Laplacian with the shift operator?
But what do you mean by shift operator?
That u tilde kt is sent to minus k1 squared u tilde.
No, it's not a shift operator. It's a multiplication operator. Yeah. No, of course we can write an explicit formula for this Laplacian. So in our case, minus Laplacian of k equals to sum of ki squared.
Okay.
Mhm. But it depends on who k is, because in principle we can work also in these cases, and so here this case will be integer numbers. Maybe it was better to use k everywhere, not n, but k. Sorry. So that it works. It looks universally, yeah, like this. Mhm.
But what type of equation are this
Hmm?
usual Poisson equation?
Yes, I've simply said that one coordinate will be considered as time. Because I was always wondering, like at the first year of university, what happens if you try to study problems for Laplace equation analogous to problems for the wave equation, because it looks like an initial idea to perform a kind of analytic continuation from one equation to another one, but it doesn't work this way actually. So it somehow works at the level of gain functions, especially in the momentum space, but not on the level of initial boundary value problems. Yes. Okay, so we can do this, and the advantage of this approach is that all these equations look the same and independently on the structure of space of boundary conditions and so on. Mm. Well, we have these equations, but now we should ask what kind of problems we can study. So let us first study the heat equation. The second one. Well, that's the simplest one. Uh, we have already studied this one-dimensional equation. So you see that everything separates between different momenta. All these equations split. Mm. And uh, uh, can you tell me how the general solution of this equation looks like? We have initial conditions. Uh, and the equation itself. This is the initial condition, and we should solve them together with a equation. So, do you remember any answer for this case? Hmm? So, for example, if yes, but how does the answer look like? Okay. If we first solve this problem for zero initial conditions and then add them like just add another term to the solution. How would you write? How would you write the solution of this equation with zero initial conditions? Yes. Oh, so we are basically solving equation dt u plus gamma u equals f of t. So if gamma equals to 0, it just integral from minus infinity to the given time. And if gamma is non-zero, we have some surprising factor in this integral. So formula looks like this. U of t is integral from minus infinity to t dt prime e to minus gamma t t minus t prime, f of t prime. Can be obtained in several different ways. But it's not the answer for our problem, because here we are integrating from minus infinity because we do not have boundary conditions. But if we have boundary conditions at t equals 0, then what should we do here? Yes, uh, and add something. Well, so what should we add? Yes. So this solution vanishes for t equals to 0, and the show conditions. So we should substitute the solution of homogeneous equation without right-hand side multiplied by something, so that it satisfies initial condition. Initial conditions. Right. So if we do this with our equation, then what do we get? Okay, till t is what? Mm-hmm.
The prime of t to the minus k squared.
Well, maybe maybe let us actually write k squared instead of Laplacian. Yes. So minus k squared t minus t prime. Right.
No, k. Yeah, yes, k.
Mm-hmm. Of t prime.
Does not f depend also on k?
It depends. Yes. Mm-hmm.
Plus e minus k squared.
Hmm? Ah, yes, yes. Thank you. Yes.
T
Mm-hmm.
times u tilde 0 k.
Yeah. Thanks. So yes, we have the solution, and now we can uh, ask the two things. Uh, the first question is, does this formula really define a well-defined function? So we wrote some formula, and we can ask whether it exists or not. So uh, uh, so if uh, t is greater than 0, then yes, of course, because this exponentials go to 0 when k goes to infinity. Then and they go they're super exponentially faster than any exponential. When k goes to infinity. But what happens if we put t less than 0? Hmm? Well, it depends on initial conditions and on the right hand side. So this situation is called a well-posed problem. Maybe let me write on the other blackboard. So we have our Laplace, we have our heat equation. And we can, in principle, study different boundary value problems, because in principle we have this domain, for example, one two-dimensional plane with t and x with t and x coordinates. And if we don't pay attention to which precise equation we are studying, we could equivalently study problems like this. We could give some boundary conditions here, boundary conditions here, and boundary conditions here, which we call in this case initial conditions. So in this case, it can be called an initial value problem. Statement is that it is well posed. Which means that if we so let us say that here we have some function u u0 of x, which means that if u0, if two initial conditions are closed, maybe I would say if two initial conditions are closed, then two solutions are closed as well. So in the sense that a solution of this problem depends continuously on initial conditions. It is easy to see that if we take two closed functions that mm, mm, uh, well, probably to prove this rigorously, we would need to. mm, No, we don't need to do this, but maybe it would be easier if you write an exact formula for this solution. But it is more or less clear that this works. Since we have a function that goes to zero, so its Fourier coefficients go to zero as well. And if you multiply these Fourier coefficients by this cutoff factors, they go to zero even faster. So we can write such kind of estimates and see that it is true. Mm. Uh, but So this was a good case. But if you know nothing about this equation, you could, in principle, just flip this picture and ask this function to be fixed at some other boundary. So we could do like this. We could put it here and call it maybe final value. But terminal value, well, or in other words, we could run this evolution in the opposite direction. So if you do like this, then this part of solution, so we would have a formula like this. Okay, tilde of t is integral from 0. Maybe we can study even a simpler case, f equals to 0. If k of t is e to k squared t u0 k tilde. Right? So these numbers are Fourier coefficients of for example, twice differentiable function. Maybe. Well, let us consider a one-dimensional case. Maybe we can ask even more. We can take a very smooth function with nice Fourier coefficients that decay according to some power law, but definitely not super exponentially. Or maybe better. Oh, it's fine. So if we consider this case and try to find the solution for any t greater than 0, uh, 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 sorry, maybe no. I should have chosen one of two options, either to change the sign or reverse time. So maybe I will not change sign, but will reverse time, saying that now t is less than 0. Yeah. Yes. So if this utility are of this kind, then you tilde k of t for t less than 0 does not exist. So so it's the most trivial case. So it does not exist from the very beginning. But in principle, we can meet other examples of initial conditions. Another example would be, uh, uh, for example, uh, mm, this one. Uh, it it is a very smooth function such that u tilde k behave as e to minus a, maybe absolute value of them less than e to a k squared. In this case, UK tilde is defined up to some time. And what is this time? Oh, sorry, I should have written inverse Fourier transform of this u of t and x. What is the time for which it still makes sense as as a function? Hmm? No, in this case, we are studying negative times. So we ask this to be something on this boundary, and we are looking for a solution in this domain. Well, in this case, minus a. Mm. So a is greater than 0. So so there is a solution that develops singularities in finite time. And mm, so third example could be something very nice where this coefficients behave like less than e to minus a k absolute value cubed. So in this case, it is defined for all times. Uh, but because this exponential does not change this behavior. But the point is that these two cases, A and C, are actually infinitely close. Because if we want to break this asymptotic behavior of Fourier coefficients, we just need to break some of the derivatives of this function. For example, if we break its 11th derivative, saying that it is only 10 times differentiable at a given point, just at one point, then its Fourier coefficients start behaving in a power law way. So we can say that there is a function for any epsilon. There is a function u a such that supremum of u a of u a 0 of x minus u c 0 of x less than epsilon. And it's absolutely sufficient to break this property because solution with one initial condition. So pictorially we can draw it like this. We have one function which is very, very smooth, and we take another function that is almost the same, and slightly break it around one point. Add some tiny cusp, or even something much smoother than this cusp. And depending on the essence of this singularity, it can either break the solution immediately, or it can produce some singularity at finite time later. So this is u c. This is u c 0. This is u a 0. So this problem is called ill-posed. What is happening here? Here is called the ill-posed problem. So it was kind of lesson one that we could learn from this study of APDs with partial Fourier transform. We can kind of slightly upgrade this technique that works for one-dimensional equations, adding momentum dependence and study asymptotics of Fourier coefficients of the solutions in the momentum space. Oh, and we can learn this lesson. And this well-posedness and ill-posedness depends on equation. But we can also learn another lesson, and this lesson will be about green functions. Are there any questions about these two problems? Okay, let us take this solution and go to the coordinate space. And we have this equation ut equals to Laplacian of u, and we know that after Fourier transform, uk tilde of t is e to minus k squared t u k of 0. Let's let's substitute. Let's take the inverse Fourier transform of this. Tilde. And let me denote it like u0k. So u0k for u of t and x is given by the integral in the d and k over 2 pi to over n. So we have this inverse Fourier transform, and now we substitute Fourier coefficients of initial conditions also as a Fourier transform. So this is this term. we will not compute this integral, but we can rearrange it a little bit. So namely, we can write it as an integral dx prime, dnx prime, u0 of x prime, and integral dnk over 2 pi to power n e to ik x minus x prime minus k squared t. So do you recognize this integral? It is structurally. Do you remember anything like this in connection to the heat equation? Well, no. We have minus k squared t, so it is absolutely convergent for any positive t, and actually very well convergent. Yes, yes, technically yes, but you can remember that yes, but I'm asking actually a slightly more general question. That this integral, even without knowing the exact formula for this integral, we can remember that it appeared as a result of some computation. So maybe let me erase this part about the Fourier transform and let me remind you that computation. Maybe even uh, even without, probably I don't want to redo it in the old way, and let us do it in a new way. So we have this first problem with non-trivial initial conditions, but we also have another problem with zero initial conditions and non-trivial right-hand side. So let us say that first solving this problem, and this u is given by this formula. So, and let us also solve another problem. I actually know this solution. So let us take Fourier transform of this. So another problem is this u t2 equals Laplacian of u2 also u of 0x equals to 0, sorry, plus f. Here initial conditions are 0. So for components of this function are given by this formula u k2 of t are given by integral from 0 to t dt prime e to minus k squared t minus t prime f tilde of t prime, like this. Right, and if we now take Fourier transform of this function, so this integral and we are substituting fk as its Fourier transform. Uh, this and now let us rearrange integrals. So we have integral in dx prime, and integral in dt prime, integral dx prime, f of t prime, x prime, integral dnk, or 2 pi to the n. I forgot the main part. Time this exponential. So I have to move this to next line. So you see exactly the same integral, right? This integral and this one. So and if speaking about computation of this integral, then of course it can be computed by completion of that a square, but the answer is the following. Let me just write it. It is 1 over 4 pi t to n over 2 a2 minus 1 over 4t x squared. So and this is called Green function. uh, so mm, so the lesson that we learn from here is the following: that there are different types of gain functions. There are gain functions that express the solution of our equation in terms of the right-hand side, but there are gain functions that express its solution in terms of initial conditions. So, uh, so uh, So it's first part. The second part is that they are expressible in terms of gain functions for the right-hand side. Maybe I can write it like this. So how does it work in this particular case? We were solving two types of the heat equation for initial within trivial initial conditions and within trivial right hand side, but now we can combine them. Uh, so u of t and x, which is a combination of these two. So it is so in one case it is an integral from over dnx. Mm, 1 over 4 pi t to 1 over 2, maybe. Oh. And here I write initial condition. This is what we are playing today. Mm. But there is also another part that we knew before. There is, oh, so this is integral in f prime. And the part that we actually knew before is this d prime dn x prime Oh. So the general solution of the heat equation was in trivial uh, initial conditions and the right hand side. So, solution to this equation of 0 and x equals to u0 of x. So it is this u given by this formula. So it solves this equation with on this boundary conditions. Do you have any questions about this?
Is the well-posed problem of the heat equation related to thermodynamics, where it's irreversible, macroscopic?
But in thermodynamics itself does not consider reversible phenomena. It is about about so, how to call this. So it's about time independent situations. If you want to include some time dynamics, it becomes physical kinetics, uh, which is reversible. So, but a heat equation is a kind of effective description of
It's like
how
a
to say.
definition of field theory for a discrete system of equal particles.
Um, I would say that it's not like even effective theory. It's a theory that ignores all distributions in the momentum space. Switch from generic distributions in coordinate momentum space to the first moment of the distribution, to integrate everything in momentum. Well, maybe it is too far from what we are studying, because there is this momentum and there are also momentum which is physical momentum. Velocity. Okay. Let us uh, uh, look at one more example where we have well-posed and ill-posed problems. Mm, what can I erase? Probably I can erase this. Go to the equation number 3. So we are studying this equation, uxx plus, let us for simplicity write plus uyy equals to 0. So more generally, it can be written as uxx plus plus n of u equals to 0. And let us try to do the same as for the heat equation and for the wave equation. So u of 0 and y, so this is x and this is y. U of 0 and y will be u0 of y. But what do you think if we continue analogy with with the wave equation? Do we need to fix something else here? Oh, in a sense, x derivative, that time derivative of this. Yes, we have some u1 of y. So it's an initial value problem. So let's now solve this equation. We have u tilde u tilde k of x plus oh, minus k squared u tilde k of x equals to 0. We could also write a green function for this equation, but I don't want to do this because it is simpler. So we have this equation. We also have an initial condition that can be Fourier transformed. So we know that u k of 0 tilde equals to u0 tilde and uk prime of 0 equals to u1 k tilde. So can you write a generic solution of this equation with this in initial conditions? Sorry, cosine, cosine, or some other function. No, if you differentiate usual exponential that contain imaginary unit, yes, yes, and it's important. So it is hyperbolic cosine k times u0 0k tilde cosine of kt plus what 1 over absolute value of k, oh just 1 over k, because everything is symmetric. Right. And now we have exactly the same problem. So if coefficients of this expansion for initial conditions behave like exponentially, if they decay even exponentially, then the solution is still developing a singularity in a finite time. Which in the continuous case, for example, or in the for finite case, like this, depending on the Fourier transform. And if and also for another initial condition. If they are not that smooth, if their Fourier coefficients decay slowly, then it can happen that the solution does not exist even for any time greater than 0. So we see that this naive boundary condition that worked for the heat equation, for the wave equation, do not work in our case. And you also see that if the sign was different, then we can simply write cosine of kt and sine of kt. Both of them are bounded by 1, so this solution would be well defined. So if initial conditions were continuous, maybe differentiable just once, then it would be sufficient to prove easily that the solution exists for any time. So is it clear? Maybe I can write it somewhere. What was 1? Oh, the equation itself looks like this, plus k squared uk of t equals to 0. And its solution is this. So if sum of 0k is convergent, so if this Fourier series for initial conditions are absolutely convergent, then UK of t is well defined. U of t and x is well defined. So a difference between these two equations. But let us now study a problem for the Laplace equation that is well posed. So these boundary conditions or initial conditions did not work. So let us study now these ones. Really fixed boundary conditions, since we fix values on one boundary and on another one. So let us say that it is value L and this is 0. So we have u0 of y and u L of y. And they are boundary conditions. So looking at this equation, can you give me a solution that solves it with boundary conditions? So I want solution of this equation with such boundary conditions, or their Fourier transform. So you can write that u mm, k of k tilde of 0 is u tilde of 0k, u tilde k of L is u tilde Lk. So can you write a function that satisfies such boundary conditions and solves this equation? So, namely, I propose, so I'm writing the corresponding coefficients times some function that equals to 1 on one boundary and equals to 0 on another boundary. And for another one, these conditions will be solved. It should be 0 on one boundary and 1 on another one. Can you guess on these expressions? Of kx yes. 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 And here actually we can do a similar thing. And what can we do? And just reverse it and write a hyperbolic sign of k L minus x, right, over hyperbolic sign of kl, right? So it is the answer. And we see that absolute value of this hyperbolic sign is less or equal than 1. So in a sense, it's similar to this situation when absolute value of cosine of kt was less or equal than 1, and absolute value of sine of kt was less or equal than 1. And the same for that ratio. So the problem is again well posed. So do you have any questions about this? So, and maybe let me in a few minutes tell a few words about the last problem, because you see we have studied two different problems for Laplace equation: ill-posed problem with the initial conditions and well-posed problem with boundary conditions. And so far we know about the well-posed problem for the wave equation with initial conditions. So there is a natural hypothesis that if you try to impose boundary conditions for the wave equation, then it becomes ill-posed, right? So, and I will not write these formulas, but simply show how to understand this. So let us consider uh, the following square. And it's important that it is square. In a sense, we have points 0, 1, 1. Yeah, so it is a square shaped. So a general solution of this equation will look like a combination. Maybe let us take here pi. So a general solution of this equation, and say that here use 0, and here is 0 as well, and here it equals to something. So the general solution of this equation looks like this combination of trigonometric functions: sine of nx times oh, let me maybe write it like this: cosine. Right? Because this is a coordinate part, and if you solve a corresponding equation for time dependence, its solution will be again sines and cosines. So with this formula, and we can notice that these functions are pi periodic. So each, so they are called normal modes. We will talk about this more later. But the point is that they are periodic. So if you consider the square shape, then by more or less by construction, u on this boundary equals to u on this boundary. So, and we simply don't have enough parameters to fix this coefficients. So if you impose arbitrary boundary conditions, then the solution will simply not exist. Maybe, wait, probably I should have, or maybe let us put here 2 pi to be on the safe side. Yeah, yes. Yeah, maybe, so the square should be fine, but maybe we should take a rectangle. but they are definitely 2 pi periodic functions. Uh, and so boundary conditions are not independent. And if you try to write formulas like this formally, then we see that these hyperbolic functions will turn into trigonometric functions. And the important question would be if sine or cosine of k times L is 0 or not. And it can approach 0, and it will approach 0 if we choose this distance in a bad way. So we can kind of have 2 types of problems for a wave equation and for a Laplace equation, and only one of them for which equation is well posed, another is ill posed. So do, do you have any questions about this? Okay, if not, see you tomorrow. So I'll probably add more problems to the file. I've just added one more, but there will be more about such kind of problems. So, thanks for your attention.